Welcome everyone to the BGAS Painting Inspection Practical Training Program. This course is designed to develop your ability to identify inspection equipment, understand coating inspection principles, and successfully answer practical examination questions. As a coating inspector, your responsibility is to ensure that every stage of surface preparation and coating application complies with project specifications, international standards, and client requirements. During this training, we will review actual field equipment, abrasives, testing devices, and inspection methods commonly encountered in industrial painting projects. Pay close attention to the photographs because many of these images are frequently used during BGAS examinations. Let's begin with abrasive identification. On this slide, we can see copper slag abrasive. Copper slag is one of the most widely used expendable abrasives in industrial blasting operations. It is produced as a byproduct of copper smelting and is classified as a nonmetallic abrasive. The angular particle shape allows effective removal of mill scale, rust, and old coatings while producing an anchor profile suitable for coating adhesion. The most important examination point is that copper slag is intended for single use only. Once blasting is completed, the abrasive becomes contaminated and should not be reused. For examination purposes, remember: copper slag, nonmetallic abrasive, expendable, single-use material. This slide shows spent or contaminated copper slag. Notice the darker appearance and contamination from rust particles and coating debris. As inspectors, we must verify that contaminated abrasives are not recycled or reused in open blasting operations. Using contaminated abrasive may introduce foreign matter onto the prepared steel surface and can lead to coating failure. A common examination question is the difference between fresh and used copper slag. Fresh copper slag appears clean and angular. Used copper slag appears contaminated and unsuitable for reuse. This slide illustrates garnet abrasive. Garnet is a naturally occurring mineral abrasive widely used in the oil and gas, marine, and offshore industries. Its major advantage is low chloride contamination and excellent profile generation. Unlike copper slag, garnet can often be recycled after proper cleaning and screening. As inspectors, we must ensure the abrasive remains free from contamination before reuse. Remember: garnet equals mineral abrasive. Low chloride content. Reusable after cleaning. This slide shows steel grit. Steel grit is characterized by its angular shape. The purpose of grit is to cut into the steel surface and create the anchor profile necessary for coating adhesion. The angular particles remove contaminants aggressively and produce a rough surface texture. A common examination question asks the difference between grit and shot. The answer is simple. Grit cuts. Shot peens. Always remember this phrase. This slide shows steel shot. Unlike grit, shot particles are spherical. The primary function of shot is peening rather than cutting. Shot is frequently used in automatic wool blasting systems where abrasive recovery is possible. The rounded particles produce a more uniform surface profile. For examination purposes, shot equals spherical particles. Peening action. Profile control. This slide shows a mixed abrasive system. A typical mixture consists of approximately 80% shot and 20% grit. The grit creates the profile while the shot controls excessive peak height. This combination provides efficient cleaning and consistent surface preparation. Many fabrication shops use this method for automated blasting operations. Remember: grit creates. Shot controls. This slide shows walnut shell abrasive. Walnut shell is classified as an organic abrasive. Unlike metallic abrasives, walnut shell is used on delicate surfaces that could be damaged by aggressive blasting. Typical applications include fiberglass, aluminum, wood, and composite materials. A key examination point: Walnut shell is generally not suitable for heavy steel surface preparation. This slide shows sieve analysis equipment. Sieve analysis is used to determine abrasive particle size distribution. Particle size directly affects surface profile and blasting performance. Oversized particles may create excessive profile depth. Undersized particles may fail to produce the required profile. As inspectors, we use sieve analysis to verify abrasive quality before blasting operations begin. This slide shows a surface profile needle gauge. The instrument measures the peak-to-valley depth of a blasted steel surface. Before use, the gauge must be calibrated and zeroed on a smooth glass plate. The measurement obtained represents the anchor profile that will provide mechanical adhesion for the coating system. This is one of the most frequently used profile measurement instruments in the field. This slide shows the Replica tape method. Replica tape captures the surface profile by compressing foam against the blasted steel surface. The compressed tape is then measured using a spring micrometer. The method is widely accepted internationally and provides reliable profile measurements. Always remember the examination formula. Measured value minus 50.8 micrometers equals actual profile depth. This slide demonstrates proper replica tape application. The tape must be firmly burnished against the blasted surface using the supplied tool. Insufficient pressure can result in inaccurate readings. Inspectors should take multiple readings across the surface and record the average value. Consistency is essential when verifying compliance with project specifications. This slide shows a surface profile comparator. The comparator contains reference surface profiles manufactured to known standards. Inspectors visually and physically compare the blasted surface against the comparator. This method is quick and useful for field verification. Different comparators are available for grit-blasted and shot-blasted surfaces. Always ensure the correct comparator is used. Rust grading is one of the most important subjects in coating inspection. The governing standard is ISO 8501-1. The standard classifies steel condition into 4 rust grades. Grade A, Grade B, Grade C, Grade D. Correct identification of the initial steel condition is critical because it influences the cleaning method and expected blasting results. This slide presents the standard rust grade reference photographs. These photographs serve as the visual benchmark for inspectors worldwide. Before specifying surface preparation requirements, inspectors must identify the initial rust grade. Accurate rust grading ensures proper selection of cleaning methods and quality requirements. This slide shows rust grade A. Grade A steel is largely covered by intact mill scale with little or no rust. The surface remains relatively protected. However, the mill scale must still be removed before coating application because coatings do not bond reliably to mill scale. Remember, grade A equals intact mill scale. This slide illustrates rust grade B. The mill scale has started to detach and rusting is becoming visible. The steel surface is beginning to deteriorate but remains less corroded than grade C or D. Inspectors should identify areas where scale lifting and rust formation are occurring. This slide compares different blast cleaning standards. Inspectors must distinguish between SAW 1, SAW 2, SAW 2.5, and SAW 3. The most commonly specified standard in oil and gas projects is SAW 2.5, also known as near white metal blast cleaning. Understanding these visual differences is essential for examination success and field inspection activities. This slide demonstrates how a grade B surface appears after blasting. Notice the significant improvement in cleanliness and uniformity. The objective of blasting is to remove corrosion products, contaminants, and loose mill scale while generating a suitable profile for coating adhesion. This comparison helps inspectors understand the effectiveness of surface preparation. This slide shows rust grade C. At this stage, the mill scale has completely disappeared. The steel surface is fully rusted and may contain minor pitting. Grade C surfaces require more aggressive blasting than Grade A or Grade B surfaces. As inspectors, we must evaluate pitting severity and verify that all visible corrosion products are removed during blasting. Remember, Grade C equals complete rusting with possible light pitting. On this slide, we observe a rust Grade C surface after blast cleaning. Before blasting, Grade C steel is completely rusted with little or no remaining mill scale. After proper blasting, all visible corrosion products must be removed and the surface should display a uniform metallic appearance. As inspectors, we must verify that rust, scale, and contamination have been completely eliminated. Any remaining corrosion products can act as initiation points for coating failure. This slide demonstrates the transformation from a heavily rusted surface to a coating-ready substrate. This slide shows rust Grade D steel. Grade D represents the most severely corroded condition defined by ISO 8501-1. Heavy rusting is present across the entire surface and significant pitting is usually visible. In practical applications, Grade D surfaces require increased blasting time, higher abrasive consumption, and closer inspection. Remember this important examination point. Grade D equals heavy corrosion with visible pitting. Here we see a Grade D surface after blast cleaning. Notice that while rust and scale have been removed, the pitting remains visible. Blasting removes corrosion products but does not remove metal loss caused by corrosion. Inspectors must ensure that all corrosion products are removed from the base of pits and cavities. A common mistake is assuming that a pitted surface is unacceptable after blasting. Pitting is acceptable provided the surface preparation standard has been achieved and the pits are free from contaminants. This instrument is known as a hypodermic needle gauge. It is used to measure blast nozzle pressure during abrasive blasting operations. Nozzle pressure directly influences cleaning efficiency, profile generation, and productivity. To obtain an accurate reading, the needle must be inserted into the blast hose at approximately 45 degrees and directed toward the blast nozzle. This detail frequently appears in BGAS examinations. Always remember: 45 degrees. Pointing toward the nozzle. This slide shows pH indicator paper. The purpose of pH testing is to determine whether a clean surface is acidic, neutral, or alkaline. After chemical cleaning or water washing, pH verification is often required before coating application. A surface that is excessively acidic or alkaline may negatively affect coating adhesion and long-term performance. As coating inspectors, we must ensure the surface condition is suitable before painting begins. This slide illustrates the Mercaquant chloride test. This test is used to detect chloride contamination on prepared steel surfaces. Chlorides are particularly dangerous because they attract moisture and can initiate underfilm corrosion. Many coating failures occur because surface salt contamination was not properly controlled. Inspectors should understand both the purpose and limitations of chloride testing methods. This slide shows the Bresle patch method. The Bresle test is one of the most widely accepted methods for determining soluble salt contamination on steel surfaces. Distilled water is injected into the patch, the solution is agitated, and then extracted for analysis. The results are used to calculate surface contamination levels. A key examination point. Bresle testing is used for soluble salt contamination assessment. This slide shows a density cup, also known as a specific gravity cup. The instrument is used to determine paint density. Density verification is important because it confirms that the supplied paint corresponds to the manufacturer's approved formulation. Any significant variation in density may indicate contamination, incorrect mixing, or product inconsistency. As inspectors, we must verify paint quality before application begins. This slide shows a Hegman grind gauge. The purpose of this instrument is to evaluate pigment dispersion within a coating material. Poor pigment dispersion can lead to surface defects, poor appearance, and inconsistent coating performance. The gauge identifies the presence of oversized pigment particles and unmixed material. A properly manufactured coating should demonstrate smooth and uniform dispersion. This instrument is a rotational viscometer. It is used to measure dynamic viscosity. Viscosity influences application characteristics, flow properties, and film formation. If viscosity is too high, application becomes difficult. If viscosity is too low, sagging and insufficient film build may occur. Viscosity testing is therefore an important quality control activity before coating application. This slide shows the Krebs Stormer Viscometer. The instrument measures paint viscosity using Krebs units. This method is commonly used in paint manufacturing and laboratory environments. Understanding viscosity measurement techniques helps inspectors verify that coatings meet manufacturer requirements before application. This slide illustrates the Ford Flow Cup number 4. The Ford Cup measures flow viscosity by timing how long a coating takes to flow through a calibrated orifice. The result is recorded in seconds. This simple and reliable method is widely used for field viscosity checks. Inspectors frequently use Ford cups to verify thinning ratios and application consistency. This slide demonstrates proper Ford cup testing. The cup must be clean and level before testing begins. The coating is poured into the cup until full, and timing starts when the flow begins. Timing stops when the continuous stream breaks. Accurate timing is essential because even small errors can significantly affect results. This slide shows an eccentric wheel wet film thickness gauge. The instrument measures wet coating thickness immediately after application. Wet film measurements allow inspectors to predict the final dry film thickness. This enables corrective action before the coating cures. The gauge is simple, fast, and widely used during coating application activities. This slide shows a comb-type wet film thickness gauge. The gauge contains calibrated teeth of varying heights. When pressed into the wet coating, the highest wetted tooth and the lowest dry tooth determine the wet film thickness range. The method is simple, economical, and commonly used in field applications. This slide shows a paint inspector gauge, commonly called a PIG gauge. The PIG gauge is a destructive testing instrument used to measure dry film thickness. The instrument cuts through the coating to the substrate and allows direct measurement under magnification. One major advantage is that individual coat thicknesses can also be determined. This is an important examination point. This slide illustrates the Saberg test drill. This destructive test method is used for coating thickness evaluation on thick coating systems. The drill penetrates the coating without damaging the substrate excessively. Inspectors use the resulting measurements to verify compliance with specification requirements. This slide shows electronic dry film thickness gauges. These are among the most commonly used instruments in coating inspection. On steel substrates, the operating principle is magnetic induction. On non-ferrous substrates such as aluminium, eddy current technology is used. Before measurements are taken, calibration and verification must be performed using certified standards. Remember: calibration first, measurement second, acceptance decision third. This slide shows a Tinsley Pencil gauge. The instrument is a non-destructive thickness measurement device used primarily on pipelines and curved surfaces. Its portability and simplicity make it useful in field inspections. Inspectors should understand both its application range and measurement limitations. This slide shows a horseshoe gauge. The instrument is another non-destructive dry film thickness gauge. Its design allows measurements on cylindrical surfaces and difficult-to-access locations. Although modern electronic gauges are more common today, understanding traditional thickness gauges remains important because they frequently appear in BGAS examinations. Knowledge of these instruments demonstrates a strong understanding of coating inspection fundamentals. On this slide, we see the banana gauge model 111. This is a non-destructive dry film thickness measuring instrument commonly used before the widespread introduction of electronic thickness gauges. The gauge operates using magnetic principles and is suitable for measuring coating thickness on ferrous substrates. Although modern digital gauges are more common today, inspectors should still recognize this instrument because it frequently appears in BGAS examinations. When identifying this instrument, remember its primary purpose is non-destructive dry film thickness measurement. This slide shows the banana gauge model 211. The operating principle is similar to model 111, however, the measuring range and calibration features may differ depending on the manufacturer. As inspectors, it is important to verify calibration before taking measurements. A coating thickness measurement is only as reliable as the calibration of the instrument used. Always inspect calibration standards before use and record verification results as part of quality documentation. This slide shows calibration shims. Calibration shims are precision foils with certified thickness values used to verify the accuracy of coating thickness gauges. Before performing dry film thickness measurements, inspectors must confirm that the gauge provides accurate readings across the expected thickness range. Failure to perform calibration verification may result in acceptance of non-compliant coating systems. A common examination question asks why calibration shims are used. The answer is simple: to verify instrument accuracy before measurement. This slide illustrates the conical mandrel bend test. The purpose of this test is to evaluate coating flexibility. During the test, a coated panel is bent around a conical mandrel, creating progressively increasing strain along the coating film. Inspectors examine the coating for cracking, flaking, loss of adhesion, or other signs of failure. Flexible coatings should withstand deformation without damage. This test is particularly important for coatings applied to components that may experience bending or thermal movement during service. This slide shows a BK drying time recorder. The instrument is used to determine coating drying characteristics. A moving stylus travels across the coating surface while the coating cures. The resulting track allows evaluation of different drying stages including surface dry, tack-free, and fully cured conditions. Understanding drying behavior is important because premature handling or overcoating may lead to coating defects and reduced performance. This slide shows the Bolletini impact test apparatus. The purpose of impact testing is to determine a coating's resistance to sudden mechanical impact. A specified weight is dropped from a controlled height onto the coated test panel. After impact, inspectors examine the coating for cracking, loss of adhesion, or other signs of failure. Impact resistance is especially important for coatings used in areas subject to mechanical damage during operation. This slide demonstrates the mechanical thumb test. This simple field test provides a quick indication of coating cure. Pressure is applied to the coating surface using the thumb or a mechanical device. Inspectors evaluate whether the coating remains soft, tacky, or fully cured. Although this method is not a precise laboratory test, it provides useful information regarding coating readiness for handling, overcoating, or service. This slide shows the Wolff-Wilborn pencil hardness test. The test evaluates surface hardness by pushing pencils of increasing hardness across the coating surface under controlled conditions. The hardest pencil that does not scratch the coating determines the hardness rating. This test is widely used for quality control and comparison of coating systems. Inspectors should understand that hardness is not the same as adhesion or flexibility. Each property must be evaluated independently.